In this webcast, we're discussing velocity versus time graphs. So on the first page of Worksheet 2C, we've got some examples of motion maps on the left, and then we're going to make the corresponding velocity versus time graph on the right. So first it says, let's make a motion map for something that's moving in the positive direction at a steady speed. And so, I'll just start the object at position 0, and let's let it go at 1 meter per second. And so as each second passes, it's moving 1 meter to the right. And I'm going to have a motion map where the arrows, the velocity vectors, are all the same length, and they're indicating a velocity of 1 meter per second. Okay, so let me come over here, and I'm going to put a scale on my time axis. This is seconds, and then my velocity, which is meters per second, I need to show a velocity of 1, okay? And that velocity of 1 occurs for 5 seconds. So my velocity versus time graph ends up being a horizontal line that is at a value of 1 meter per second, and it goes for 5 seconds. Okay, let's go to the next one. So here it says the object is standing still. Okay, so I'm just going to put it at some location. Let's say position 3 meters here, and it stays there for 5 seconds. Okay, the dots stack because it's not moving, and it's just staying at that position. So since it's not moving, the velocity is 0. And so I'm going to show the velocity versus time graph as just a horizontal line, and it's for 5 seconds with a value of 0 meters per second. So you're probably starting to get the idea that when an object is moving at a constant velocity, the velocity versus time graph, it's going to be a horizontal line, right? Because it's showing that the value of the velocity is not changing over that time. Okay, let's do one where the object changes direction. So here, the object moves in the negative direction at a steady speed for 3 seconds. Then it stands still for 3 seconds. So I'm going to have it start all the way up here at position 5, and I'll have it come back in the negative direction for 3 seconds at a speed of 1 meter per second, and then when it reaches position 2, it stands still for 3 seconds. It just stays there. Okay? So now I need to show that the velocity is -1 for those first 3 seconds. Remember that velocity is a vector, and the sign, whether positive or negative, tells you information about the direction that it moved. So if it's moving in the negative direction, we have a negative velocity. Okay. So now I'm going to show a velocity of -1 because it was moving in the negative direction for the first 3 seconds. And then at time 3, it started pausing. It didn't move for the next 3 seconds. And so I show a velocity of 0. Okay, so notice that there is a gap here. I don't have a continuous graph. This gap is okay. It just means that I had a sudden change in the velocity. Okay, so anyway, a position versus time graph must be continuous, but velocity versus time graph, the gap is okay. Okay, let's do another one here. The object moves in the positive direction for 3 seconds, and then it reverses. It does not pause. And then it moves back in the negative direction at the same speed. Okay, so I'm going to have it start at position 0, and let's let it go at 2 meters per second for 3 seconds. So I get longer velocity vectors because it has a bigger speed. And then it does not pause, so I don't stack a dot at position 6, but it immediately turns around and starts coming back at the same speed in the negative direction. Okay, so let's see here. So now I need to show a positive velocity of 2 meters per second and a negative velocity of negative 2 meters per second. Okay, so for those first 3 seconds, when it's moving in the positive direction and it's moving 2 meters every second, so I'm going to show a velocity of 2 for the first 3 seconds. And then it immediately turned around without pausing and went back in the other direction at a velocity of negative 2 meters per second. So I have this big gap, but I know that that's okay. Okay, let's go to the next page here. Now, instead of motion maps, we have position versus time graphs on the left, and we're going to build the corresponding velocity versus time graph on the right. So in this first one, number 5, I see a linear graph, and it starts at position 0 and it goes to position 4 in 4 seconds. So the velocity is or actually let me do the displacement first. So the displacement over this whole trip, remember, is the final position minus the initial position, and so that is 4 minus 0, it's 4 meters. So the velocity is that displacement divided by the elapsed time, and so it went 4 meters in the positive direction in 4 seconds, so the velocity is 1 meter per second. Okay, so when I'm showing my velocity versus time graph, I'm showing a velocity of 1, positive 1, for 4 seconds. Okay, let's look at the next one. So here, we've got a little bit more complicated motion. See how the slope changes? First, it is moving in the positive direction for the first part of the trip, and then it turns around. It does not pause, but it turns around, and then it moves in the negative direction. Okay, so I'm going to call this part A of the trip and this part B. So in part A of the trip, the displacement is the final minus initial. Well, for part A, the final position is up here at position 4, and it started at position 2, so its displacement was 2 meters. And so its velocity was the 2 meters that it moved for that part of the trip, and the time for that part of the trip was 2 seconds, so it was 1 meter per second. For part B of the trip, the displacement, it ends up at position 0. I know this point is next to that 4, but remember we have to read the position off of the vertical axis. So the final position was 0, and it started this trip up there at position 4, so its displacement was negative 4 meters, And so its velocity is that displacement divided by the time that elapsed during part B, which was 2 seconds, and so we have a velocity of -2 meters per second. Okay, so when we go to do the velocity versus time graph, for the first 2 seconds, the velocity was a +1. It was moving at 1 meter per second in the positive direction. But for part B of the trip, it had a velocity of -2 because it was moving 2 meters down or in the negative direction every second for those 2 seconds. Okay, let's go on to another one. So here, it's always moving in the positive direction, but see how the slope changes? Here in part A of the trip, the slope is steeper. It's moving faster. Here in part B of the trip, the slope is a little less steep, so it slows down a little. So in part A, the displacement for part A, let's see, the final position of part A is position 2, and the original position was 0, so it went 2 meters. And so the velocity of part A is that 2 meters that it moved in 1 second, so it's 2 meters per second. In part B of the trip, the displacement is 4 minus 2. It moved 2 meters up, and it did that in 4 seconds, so the velocity is 2 meters over 4 seconds. It's 0.5 meters per second. So our velocity versus time graph, for the first second, which is part A of the trip, our velocity was a +2. And then for the second part of the trip, which lasts 4 seconds, the velocity is 0.5. Okay, so for many graphs, both the slope of the line and the area between the line and the horizontal axis have physical meanings. So let's recall what the slope of a position versus time graph is telling us. Okay, and we put this in our model summary, but we know that the slope of a position versus time graph equals the velocity. The magnitude, that just means the amount of the slope, equals the speed, and the sign of the slope, and by that I mean either positive or negative, identifies the direction of motion. Okay, so we've known that, and we've been using that information. Let's see, but now let's talk about what this information means on a velocity versus time graph. So let me get this over here. So first, it asks us to think about, when we look at the velocity versus time graph, what are the units for 1 square of area on that graph? Okay, so let's go look at that. Here is 1 square on the graph. Here, let me show. I'm coloring in 1 square in the yellow. Okay, so I'm going to calculate what that area is. You know, the area is just the length times the width. Well, so my length is 1 meter per second, and then the other dimension is 1 second. Do you see how the seconds are canceling here? And so the area of 1 square on the velocity versus time graph has the units of 1 meter. This is the units of displacement. And so that's a big clue as to the meaning of this area. And so let's go up and check here. So here in this first graph, if I looked at the area between the x-axis, remember I identify the x-axis as, you know, where the origin is. Okay, so this area, it is 1 meter per second high, and it is 4 seconds wide, and so the area is 4 meters. And I can see that, let me get a better color. Maybe yellow is the best color. So 4 meters, that was the same as the displacement, right, that I found from the position versus time graph, taking final position minus initial position. Let's see if that works for other graphs. So here I had motion in 2 directions. So for part A of the trip, the area between the x-axis and the graph is this, and then for part B of the trip, the area is actually under the x-axis, okay? So for part A, the area is 1 meter per second times 2 seconds, so that was 2 meters. Oh my goodness, look at this. This 2 meters matches the displacement for part A of the trip. Let's see if that works for part B. The area, now the height, if you will, of this shaded area is negative because it's under the x-axis. So I have negative 2 meters per second times 2 seconds. Okay, so that's an area of minus 4 meters. And that minus 4 matches the displacement for part B of the trip. And so if we kept doing this, we would find that the area always equals the displacement. And so let's summarize that by writing a statement about it. Okay, so the area between the velocity versus time graph and the x-axis equals the displacement of the object. Let me move this over here. And let me just say one other thing. What if we wanted to find not the displacement, but the distance or path length? The distance or path length equals the sum of the absolute values of the areas between the velocity versus time graph and the x-axis. So let's go up and look at that example where it changed directions right here. Number 6. So we had a trip in 2 parts. First it went in the positive direction, and so it had a positive displacement, and then it moved in the negative direction, and so it had a negative displacement. The total displacement over the whole trip would be the final position minus the initial. It ended up at position 0, and it started at position 2, and so we have a total displacement of negative 2 meters. But the distance moved was 2 meters in the positive direction plus 4 meters in the negative direction, so it moved a total of 6 meters. Okay, let's see if we can get that over here from the areas. So the total displacement equals the area of part A plus the area of part B. So it's 2 meters plus a negative 4 meters. It's negative 2 meters. And see how that value matches with this value? Okay, but what about the displacement? Oh, I'm sorry, the distance. The distance that this thing moved equals the absolute value of the area of A plus the absolute value of the area B. And so it would be the absolute value of 2 plus the absolute value of negative 4. It would be 6 meters. And again, we see that this distance equals the distance that we would have gotten from the position versus time graph.